Yes, I'm Chuanxiong from Microsoft. It's unfortunate that the first author, Yiming, cannot make it. So he's the one that did the actual work and prepared the slides. So this work was done when he was a visiting researcher at Microsoft Research Asia. So it is also a joint work with Dongsheng, Richu, Haitao, and Yongqiang. So this presentation is about Cubic, which enables fast failure detection and recovery in distributed in-memory storage systems. So we all know that storage is an important component to various cloud computing systems. So typically, people use storage systems as shown in this figure. Right? The application services access the storage system by some kind of cache system in the middle. So it is becoming increasingly hard for disk-based storage systems to meet the needs of demanding cloud computing systems because of the I/O latency and the demanding bandwidth. And also, the cache system in the middle may cause cache consistency issues as well. As a result, in recent years, we are seeing a rising of many in-memory storage systems in which all the data is kept entirely and permanently in the RAM instead of the disk. For example, in RAM cloud, InfiniBand is used to achieve tens of microsecond I/O latency, and CRAM, which is actually is publicly available in-memory system that you can put tens of terabytes of data. So typically, it's online game data. And Redis, of course, is an in-memory key-value store, which provides a very rich data model. For these in-memory storage systems, fast failure detection and recovery is kind of critical for high data durability and availability. However, to achieve this fast failure detection and recovery, several network-related challenges need to be addressed. So the first one is false failure detection. So we all know that various transient network problems like TCP incast and temporary hotspots due to network congestion can happen all the time, right? So this will make the heartbeats, among the servers less reliable, or even be dropped or be significantly delayed. So as a result, it's difficult to distinguish the real server failure from these false signals. The second challenge is the recovery traffic congestion. Fast failure recovery typically requires an aggregate recovery bandwidth of very high bandwidth, typically tens of gigabytes per second or even higher. For both the disk I/O and the network I/O. So if the distributed recovery takes place in a random and unrightly manner, then the recovery flows may traverse very long paths and may collide with each other, so resulting in very long recovery time. The second one is the Tor switch failures. So typically, in data centers, a server has only one port to connect to a top-of-rack switch. So if the top-of-rack switch fails, for example, due to server failure, so it actually can happen quite frequently. In that case, the whole set of servers will be considered dead and unreachable. So as a result, we will need to recover data for these tens of servers, so which takes quite a long time. So to address these challenges, we propose the CubicRing structure. So the idea of Cubic is to restrict the failure detection and recovery into one hop. so as to improve failure detection accuracy and also to avoid the recovery traffic congestion. So in our design, we use a multi-homed cubic network topology. Hence, even a Tor switch fails, the switches can still connect to the network via the other ports. So next, I will present the cubic ring in 3 parts. Namely the cubic structure, and second, how we handle the failure recovery, and then the evaluation results. So let me start with from the first one. So in this work, the storage model we use is this primary recovery backup model. So as you can see in the figure, there are primary servers which actually serve the queries from the users. And there are backup servers which basically act as the replicas. And there are recovery servers. So when the primary servers, the recovery servers will try to rebuild the data for the primary server. So basically, this shows how the write works. So when users write data into the system, it first writes the data to the primary server. Then the primary server will replicate the result to the backup servers. So read is much simpler. It just needs to interact with the primary server, and the results go back to the users. So once the primary server fails, so then the backup server, the recovery server come into play. So they will reconstruct the data for the primary server from the backup servers, and because we want to improve the backup, the recovery performance, so typically for one primary server, we'll use multiple backup servers in this case. So this is also the model used by RamCloud and other in-memory storage systems. So in this case, the primary servers, backup servers, and recovery servers, they are randomly placed into the network. Hence, they cannot handle the network-related challenges as we mentioned before. So to address this problem, our idea is to restrict the failure detection and recovery just within a very small possible range. In our case, it's just within 1 hop. So we improved the basic primary recovery backup structure to a directly connected tree structure. So the idea here is quite simple, right? So suppose for every primary server, we construct a set of backup servers which are just 1 hop from the primary server. And for every backup server, we construct a set of, for every recovery server, we construct a set of backup servers which are just 1 hop away from the recovery server. And of course, they are two hops away from the primary server. So that's the idea. So then the next step is, so because in our network, every server needs to carry out 3 roles, namely the primary, recovery, and the backup. So if you think about, you will end up with quite a lot of these kind of directly connected trees. So the next task is actually to embed all these directly connected trees into the physical network, right? Because the super symmetrical nature of the problem, so it's very natural to think about that. Actually, we can leverage this generalized hypercube to do this kind of work. So in our work, we are leveraging the B-cube. So B-cube is a variant of this general hypercube. So here we show how a B-cube looks like. So a B-cube network is constructed, NK network is constructed from N B-cube NK-1 network. So this example shows how a B-cube for one network is constructed from 4 B-cube 4-0 networks together with 4 switches in this case. Okay. So on top of the B-cube structure, then let's construct the cubic ring structure. So the cubic ring has 3 layers of rings, namely they are primary ring, a recovery ring, and backup ring. So the primary ring is simply composed from all the servers in the system. So it's a kind of a logical concept, right? So basically, the primary ring is also the place that will hold the whole key space of the storage system, right? So on top of the primary ring, so we construct the recovery ring. So now let's pick up a primary server. In this case, it's server 00, and all the directly connected servers of 00 become its recovery server. So all the recovery servers then form a ring, so which we call recovery ring, right? So then, as you can see, it has 6 recovery servers to form a recovery ring. So then, for every recovery server, so all its one-hop neighbors form a backup ring. So in this case, so this recovery server has 3 backup servers, which forms a backup ring. Of course, every recovery server has a backup ring. So this ends up, with quite several backup rings. So this is how the cubic ring is formed. So these are some properties of the cubic ring. So the first is that the number of the primary servers is actually the number of servers in the system, in the B-cube network, right? And for every primary server, the number of recovery servers is n-1 times k plus 1. And also, the number of backup servers for every primary server is this number. So giving you an example, for a B-cube 16.2 network, we will have 4,096 primary servers, and every primary server will have 45 recovery servers and 675 backup servers. So that's typically it's a very big numbers, to do recovery. So next, let me describe how failures are handled in cubic ring. So the primary servers periodically send heartbeats to their recovery servers. So if a recovery server cannot receive any heartbeats for a period of time from its primary server, it will report this kind of event to a coordinator. So when a coordinator collects quite a lot of such events from the recovery server, it can make a kind of the decision to decide whether the primary server is gone or not. If it decides that the primary server is gone, so it will be able to initiate the recovery process. So this figure shows the recovery procedure. So because every server has 3 roles, the primary role, the recovery role, and the backup role. So basically, when a server fails, so for recovery, we actually need to carry out 3 steps for the recovery. So the first step, of course, is to carry out the recovery for the primary server failure. So for primary server failure, we have 2 steps. The first is to, in this case, let me use an example to go through this. So in this case, we use the red color to denote primary server failure, okay? And we use the green colors to denote the recovery servers of this primary server. So in this case, because the primary server fails, the recovery servers need to reconstruct the data from the backup servers, right? So in this case, it actually fetches data from the backup servers of the red node, and after that, basically the previous recovery server will become the previous recovery server now will become one of a new primary server, and it also has the data reconstructed. The second part of the primary server failure recovery is to recover the backup data. So in this case, server 0, we still use server 0 failure as an example. Right. So now, after the primary server recovery, so server 01 becomes a new primary server, and server 11 once was a backup server, now becomes a recovery server. So because of its new role, it needs to move its backup data to the other backup nodes. So after that, the primary server failure recovery is done. So the second part is to recover from the recovery server failure. So again, we still use server 00 as an example. So in this case, 00 is the recovery server of the red node 10, right? So after 00 fails, so now because the 01 becomes the new recovery server, so it's in this case the blue backup server 10 of 00 needs to move its data to other backup servers of the red primary server. So in this case, 10 needs to move its backup data to the blue nodes 12 and 13. So the next step of the recovery is the backup server failure recovery. So again, we still use the example that 00 fails, but now in this case, it becomes a backup rule of the primary server 11. So after 00 fails, so now the primary server needs to find new backup servers to back up the data which it has. So in this case, it will send the backup data to the new backup servers. For example, in this case, it sends the backup data to 02 and 03, and also it can send the data to 20 and 30, because all these servers are on the same backup ring as the failed 00. Okay, so after that, the whole recovery procedure is done. So this table summarized server failure recovery. So as you can see, for almost all the recovery procedures, the data communication can be finished within just one hop, except the backup server failure recovery. In that case, actually, it needs 2 hops. But in this backup server recovery, it can be performed after all the other recoveries have complete, so that there's little impact on the availability of the whole system. Because after the primary server recovery is done, so the system actually can come back and serve traffic, right? So basically, the backup recovery does not contribute to the availability of the whole system. So next, let me introduce the evaluation of CubicRing. So we have built a Memcube system based on the CubicRing structure. So it's implemented by extending memcached. So it has roughly speaking, it has these 3 components. And we have built a testbed, so which it has 2 networks, fat tree and Bcube. Fat tree is used to run RAM cloud so that we can compare Memcube and RAM cloud performance. So the first experiment we do is the server failure recovery. So as you can see, Memcube can recover 48 gigabytes of data in just 3.1 seconds. So as a comparison, so using fat tree, RAM cloud has a much longer recovery time, both on oversubscribed tree and the full bisection bandwidth fat tree. So this is because in fat tree, the number of hops that the flow needs to traverse in this case is much longer compared with Mem cloud. And due to hash collision, so the throughput is much slower. So the recovery time becomes much longer. And also we have used the simulations to study the larger networks. So Memcube always has very small recovery time. So this is expected because, anyway, in most of the cases, the recovery is just within 1 hop. So we have studied the performance of the number of recovery servers versus the throughput and the k-space fragmentation. As you can see, with the number of recovery server increases, that we actually can see the aggregate recovery throughput increases linearly as well. But because you use much more number of recovery servers, so the k-space actually got more fragmented. Also, we have studied the number of backup servers that we need. So the study shows that with more than 4 backup servers, so the backup system will not be the bottleneck. So this is a brief related work. So we have kind of 2 pieces of related work. The first one is in-memory storage system. The second one is how do you do failure detection and recovery. So in summarize, I think basically our work is just to try to improve these systems by leveraging the physical proximity so that we can do recovery and detection much faster. So this is the conclusion. So basically in this work, we have proposed the CubicRing. So it exploits network proximity to restrict the failure detection and the recovery within just 1 hop. And we have built Memcube on top of CubicRing as an in-memory key value store system. So Memcube can leverage the nice properties of CubicRing and at the same time tries to maintain the CubicRing data structure even we have several failures. So with that, I will stop here and take questions. Thank you.
Hi, I'm Edward from Cornell.
Yep.
And correct me if I'm misunderstanding your protocol, but it seems that you have every server in your data center playing multiple roles. It's a primary for something, it's also a backup for something, and a recovery for something else, because you assigned all the servers as primary for something. So doesn't this mean that if a single server fails, then you actually have 3 simultaneous recovery processes going on at once? Does your results for the recovery time account for how long it takes all those recovery processes?
Yeah, this actually is so this is a good question. Yes, so basically in CubicRing, a server actually takes 3 roles, the primary, backup, and the recovery roles simultaneously. But this does not necessarily mean that basically the recovery process is carried out simultaneously for all of them at the same time. So what we did is try to recover the primary role first, so that we can. So basically, once the primary role is back, so then the primary server can begin to serve traffic to the users. So then our system's availability will come back online as soon as possible. Then after that, we can do the rest of the recoveries, which can be at that time, because the primary server is already there running, so that we have much more time to do this. And also because we have multiple backup servers, so even one is gone, it's no big deal. We still have some time. So basically, which means that we can do this kind of backup in the background.
Okay.
Thanks.